Good morning, children. Nice to meet you again through this video. I just want to give the information about your next test. It will be on October 20th, that is next Tuesday. Zoom test 2. Okay, so syllabus will be chapter 3, part D and E, and chapter 4, A part. Chapter 3, D and E part, and chapter 4, A part. Okay, so please note this and start preparing. The test will be on next Tuesday during Zoom class. Okay, so today we have to start with this new chapter, pressure in fluids and atmospheric pressure. Again, part of it, little bit of it you studied last year. Remember, pressure is force upon area, all those formulas we studied. But this here we are going to exclusively study about pressure in fluids. Now, generally, when we talk about pressure, what is the formula for pressure? Pressure is equal to force upon area. Force per unit area. Force is also called as thrust. So thrust upon area is called pressure. Okay. So thrust is basically the force exerted by a body and per area of cross section. Okay. So thrust is the force acting normally on a surface. Then thrust exerted by a body is basically equal to the weight of the body. Now suppose if this book is on this table, okay, the thrust exerted by this book will be its weight. Basically its weight. Weight is what? Force of gravity. That will be equal to its the thrust. Okay. Then SI unit of thrust is Newton. Being force, its unit is Newton. Then come to pressure. Pressure is thrust per unit area of surface or force per unit area of surface. Pressure is equal to thrust upon area or force upon area. SI unit of pressure is Newton per meter square or Pascal. Symbol will be capital P, small a. Newton per meter square or Pascal. Nm minus 2 also we can write. Okay. Then define 1 Pascal. When do you say the pressure is said to be? When 1 Newton force acts on a area of 1 meter square, then pressure acting on it is said to be 1 Newton. 1 Pascal is the force on a surface of area 1 meter square by a force 1 Newton acting normally on it. There are other units of pressure. They are bar and millibar. Okay. 1 bar is 10 power 5. They are bigger units basically. 1 bar is 10 power 5 Newton per meter square and 1 millibar is 10 power 2 Newton per meter square. Okay. Okay. There is atmosphere. Okay. That we will see in the B part. Okay. So factors affecting pressure. Now from the formula you can say pressure is directly proportional to force and pressure is inversely proportional to area of cross section. This means as force increases, pressure also increases. As area increases, pressure decreases, and as area decreases, pressure increases. We had lots of applications based on this. If you remember, camels have broad feet. Why? Increase the area, decrease the pressure, so they can walk easily. Army tankers, they have caterpillar wheels, the broad wheels. When increasing area, pressure is decreased. It is very difficult to walk on a pencil-heeled sandal or a shoe. Why? Area of contact decreases, so pressure increases, so balancing becomes difficult. Okay. Now this is mainly about pressure in solids. All that we saw so far is pressure in solids because only solids can exert a force due to its weight. Only solids exert a force on the base. You remember last year itself I remember telling this to you very clearly. Solids exert a Suppose if there is a solid can exert a pressure only at the base because of its weight. Because I keep on this table, it exerts a force and because of that, it exerts a pressure. Okay, so we're not going to go in detail about it. Just study these two definitions of thrust and pressure and come straight to pressure in fluids. The chapter actually starts with pressure in fluids. Now, what's the main difference between pressure in solids and pressure in fluids? Solids can exert pressure only at the base, but fluids, which includes gases and liquids, they exert pressure in all directions. They exert pressure in all directions. Okay, so suppose you take a liquid in a beaker. Constantly this liquid is, the molecules are moving here and there. Therefore, it exerts pressure on the sides of the container. It exerts pressure on the base and also on the sides of the container. So, we can say fluids exert pressure in all directions because the molecules are constantly moving. Whereas solids exert pressure only at the base. So, that's the main difference. Okay, a fluid contained in a vessel exerts pressure at all points and in all directions. So there is an experimental verification. This you have studied in lower classes. Okay, just go through it, that's enough. Now we come to the formula for pressure exerted by a liquid column. Formula for pressure exerted by a liquid column. It's basically from this only, but they have considered a cylinder kept floating inside a liquid, okay, and it is exerting a pressure. Okay, so this cylinder is of height h, and we have to find the pressure exerted by this at this height. At this, it's not a cylinder. We are considering this water, this much of water we are taking. Okay, we are assuming this much of water to take a particular area of cross section. We are assuming this much of water, and how much pressure will it exert in this particular area. Okay, so thankfully the derivation is not needed. Okay, so you can directly remember this formula. Pressure exerted by fluids is equal to H into rho into G. H is the depth of liquid, rho is the density of liquid, and G is acceleration due to gravity. Okay, so this liquid, because of this height h, it will exert a pressure on its base. Okay, that pressure, if I have to calculate, I have to multiply this h with the density of this liquid into acceleration due to gravity. If I want to calculate the pressure at this height, suppose if I want to calculate the pressure at this height, then at this place, if you want to calculate the pressure at this place, I just have to take this height, the height of water surface above it. Okay, so this formula you will remember, and then there is a note given here. Since actually atmospheric pressure will also be acting. What is atmospheric pressure? Pressure exerted by the atmosphere on anything on the surface of Earth. Now, there is an atmospheric pressure. Its value is nearly 10 power 5 Pascal. So, accurately means exactly if we have to calculate the pressure, if I have to calculate the pressure at this height, that will be, the total pressure will be atmospheric pressure plus H rho G. So G. Okay, because this is already acting. It's an invisible thing, but it's already acting. So you have to get an accurate calculation, you have to add this also, atmospheric pressure plus pressure due to this height h, which is H rho G. So this is the expression that you get for total pressure if you consider. Okay, so if they ask you how will you calculate the total pressure in a liquid, then you please write atmospheric pressure plus pressure due to liquid column P naught plus H rho G. Simply if they ask pressure due to a liquid column, write H rho G. Okay, then Once we study the formula, then comes factors affecting. What are the various factors affecting from the formula? So it is directly proportional to depth of liquid, directly proportional to density of liquid, directly proportional to acceleration due to gravity. So liquid depends directly on the following three factors: depth of point below the surface, density of liquid, acceleration due to gravity. Generally, in a particular place, acceleration due to gravity will be constant. So basically, it will depend on these two things only. Okay, then factors that do not affect. Okay, so there are some things that do not affect. One is shape and size of the vessel. Now, I could have a broader vessel, and I have to calculate the same height. Now, suppose you take this as 10 centimeter. So I have to take, liquid is also the same, but the vessel is broader. Okay, and the height is again the same. In this case also, pressure exerted will be the same like this, because when I divide it by area, because area will also increase, right? So finally, the pressure per unit volume in a particular area, the pressure exerted will be the same. Okay, so if height is same, pressure will be same. Even though size and shape are different, never mind, as long as the depth is same, pressure will be same. So pressure inside a liquid does not depend on shape and size of the vessel, then area of surface on which it acts. Okay, then laws of liquid pressure. Okay, there are few conclusion, the few laws you have to remember. Okay, just you have to memorize it as such. Inside the liquid, pressure increases with increase in depth. That is based on this formula. So as depth increases, okay, the pressure here will be more than the pressure here, because the depth is more, pressure will also be more. Pressure here will be more than the pressure here. So as depth increases, pressure also increases. Then in a stationary liquid, pressure is same at all points on a horizontal surface. Okay, so stationary liquid. Okay, so you have water in a beaker, it is at rest, means, and at a particular height on a horizontal plane, means you take a particular height. Okay, this at this particular height, at this point, this point, this point, this point, this point, this point, at all these points, pressure is same. Okay, pressure is same at all points on a horizontal plane, a particular horizontal plane at all points, because basically each point is at the same depth from the surface. So that is the thing. Then pressure is same in all directions about a point inside the liquid. Pressure is same in all directions about a point inside the liquid. In the sense, you choose a particular point, this particular point, the pressure exerted on this point in upward direction, downward direction, or sideways, the pressure exerted will be the same in all directions. At this particular point, pressure exerted at the top, bottom, left, right, all will be same. So pressure is same in all directions about a point inside a liquid. Fourth one, pressure at same depth is different in different liquids. It increases with increase in density. This also depends on the factor, depending on the factor. Then the last thing, a liquid seeks its own level. Liquid seeks its own level. This means last year I remember I explained you there is particular apparatus called connecting tube, which has tubes of different shapes. Okay, so now if I pour water in one of the things, it will not be that this will fill first, then this will fill. No, how much ever water I pour, the level of water will rise equally in everything. Okay, it will rise like this, then like this, like this. Okay, that is called, means liquid always tries to seek the same level. It tries to seek the same level in all the things, all the containers. Okay, so these are the laws of liquid pressure. Then come to the applications of liquid pressure. Okay, so we have 5 applications. Um, the first one is pressure at a certain depth in sea water is more than that of river water. You know, density of sea water is more than density of river water. So this, in B part you will be seeing that in detail. Leave that. Come straight to the second one. The wall of a dam is made thicker at the base, at the bottom. So you all would have seen that dam's wall will be like this. Okay, the width of the wall will keep increasing as you go towards the base. Reason why? So as the depth increases, okay, here the pressure exerted at this height, at this point, will be only due to this height water, which is less, whereas pressure exerted at this point will be due to this much height of water, which will be very high. So as you go deeper, pressure exerted on the sides of the wall is very high, and if they are not broad enough, they can break. So to withstand such high pressure, they are made broader. See the reason. First point, the reason is that pressure exerted by liquid increases with depth. Thus, as depth increases, more and more pressure is exerted by water on the wall of the dam. Second, a thicker wall is required to withstand a greater pressure. Therefore, the wall of a dam is made thickness increasing towards the base. Water supply tank is placed high. Even in a house, the tank, okay, the tank that supplies water will be always at the top, right? And even in an area, if for a particular locality there might be a huge water tank, and that will be really high, high above all the, okay, why? Because, so this is the big tank of a locality. Okay, this is the tank of a particular locality. It will be at a height. Now there will be different houses. So one house has a tank here, another house has a tank maybe at little height, like lesser height. So one thing why it is increased to this height is, as you raise this height, the pressure exerted, the pressure on this liquid will be very high. Pressure will be very high. You would have observed this in the lowermost tap of your house. Okay, in the lowermost tap of your house, the pressure of water coming will be very high. In the lowermost tap of your house, the pressure of water coming will be very high. Now when the tank gets empty, suppose remember one day tank got empty. Now all the pipes, slowly this pipe, no water is coming, this pipe, no, okay, you have different pipes at different level. Okay, so this pipe, no water was coming, this pipe also stopped, no water came. Maybe the lowermost pipe, little bit water will come, because the pressure of liquid will be very high at this height, because the height of the liquid is at a very higher height above the ground. Okay, now basically based on increase in depth increases the pressure. The reason is that as greater is the height of the tank, more will be the pressure of water in the taps in a house. Generally, that's why they place the tanks even in the houses as high as possible. More high the tank is placed, more will be the pressure of water coming in the taps. If you keep it lower, okay, there are some places you would have seen, they just have a tank down and then they will have a pipe to take water. The pressure of water coming will be quite less in this case. Thus, for a good supply of water, the height of the supply tank must always be a few meters higher than the level at which supply of water is to be made. Another thing, if the water has to fill in everything, now from this water will go to this tank and then to this tank from all the tanks. So, if only this is at a greater height, it will try to seek its level. In that way, it will fill everything. It will try to fill everything. Okay. Then the third application, diver's suit. You know, sea divers, they have to wear a special protective suit when they go into deep sea, because as depth increases, the pressure exerted by liquid increases. So the pressure will become more than the blood pressure. To withstand that high pressure, they have to wear a special protective suit made from glass reinforced plastic or cast aluminium. Now that suit will have a kind of a layer of air in between, okay, which will create a artificial pressure, which will create an artificial pressure which will be nearly equal to the blood pressure, so that your body won't get crushed. Okay, this is a very important. I don't know whether you have observed. Next time, please observe carefully. Size of air bubble inside water rises as it, okay, especially in an aquarium tank. If you see a bubble which rises from below, it might be small in size, but as it comes up, its size keeps on increasing, and finally when it comes out, it's going to break. Okay, why does its size keep increasing? Why is the size of air bubble increasing as it goes higher? Okay, the first point, when the bubble was here, the pressure was huge. Okay, because this is water, so pressure on this is high pressure. When it was here, high pressure is acting. Pressure is high. As the bubble goes up, pressure decreases. Pressure decreases. Now you know, according to Boyle's law, you would have studied in chemistry, pressure is inversely proportional to volume. That means at this point, pressure is high, that means volume will be low. But as it goes higher, because pressure decreases, volume of the bubble will increase, or the size will increase. Hope you got it. So 3 points are there. When the bubble is at the bottom of lake, total pressure exerted on it is very high. You need not write all this, children. If you want, you write, but otherwise it's enough if you write. When it is at the bottom, total pressure is very high. Second point. Okay, the first point itself. But as the gas bubble rises due to decrease in depth, pressure due to water column decreases. First you will say when it is at the base, the pressure was very high, but as it rises, pressure will decrease. Second point. According to Boyle's law, volume of bubble increases due to decrease in pressure. Okay, pressure is inversely proportional to volume. That's what Boyle's law says. Therefore, bubble grows in size. When the bubble reaches the surface of liquid, total pressure exerted on it becomes minimum, and so the size of the big bubble when touching the surface becomes maximum. I hope you have understood this. So, definitely one of these applications or consequences come in the test. Okay, so please study them clearly. The last topic in A part is transmission of pressure in liquids. Transmission means how does liquid pressure travel, or transmit means move from one place to another. That is given by a scientist called Pascal, and so it is called Pascal's law. Now Pascal's law states that pressure exerted anywhere in a confined liquid is transmitted equally and undiminished in all directions throughout the liquid. Pressure exerted anywhere in a confined liquid. Okay, it should be in a confined liquid, not in a open tub ka or river ka liquid. No, this doesn't hold good for that. It should be in a confined liquid. Is transmitted equally and undiminished in all directions throughout the liquid. Now, to demonstrate Pascal's law, you can imagine a flask like this, which has tubes from different heights. Can you see? These tubes are coming from different heights. Okay, and I take water in this, and there is a piston. As I push this piston inside, I exert pressure on this, and this pressure is now transmitted, means distributed to all these pipes. And even though they are at different heights, okay, the pressure exerted will be the same. How do I know that? If you see the height of water, jet of water reaching the same height, okay, this was the level of the tube, and water coming out of all the 4 tubes were coming out only till this height. That means the pressure of this liquid coming is the same in all 4 liquids. So that's what the law says. When I apply pressure at one point, it is equally distributed in all directions. Okay, so there are 3 points in this law. Please mark it as I marked here. Pressure exerted in a confined liquid, transmitted equally and undiminished in all directions throughout the liquid. Okay, And this all has been cancelled for you in the syllabus, application of Pascal's law. So after this, the whole thing is cut off. So with this, A part is over. Thank you, children. Start preparing for the test. See you in the Zoom class. Bye.